Hello and welcome. Grab a comfortable seat, take a deep breath, and let's just relax for a second. Today, we are going to dive into something that might look incredibly tricky at first glance, but I promise you, it's actually quite beautiful once we break it down together. I know mathematics can sometimes feel completely disconnected from our daily lives, but the underlying logic we're about to explore, it's literally the hidden machinery behind so much of our modern world, from calculating complex shopping discounts and accurately measuring irregular land partitions, to advanced building design, and even compressing the data on your smartphone so you can stream videos seamlessly. So we are going to demystify cubic polynomials today, taking it one calm, easy step at a time. Now, if you've ever opened a math textbook, seen a long, winding equation starting with x cubed, and felt an immediate wave of anxiety, listen to me, you are definitely not alone. It can absolutely look like an alien language. But, just like any language, it has a basic grammar. Today, I'm going to act as your personal tutor. We're going to crack that code together, gently and logically, so you can walk into any exam feeling completely confident. Before we even think about formulas, I want you to visualize something. Picture a roller coaster track with a distinct, steep peak and a sweeping valley. That rising and falling S-curve shape? That is exactly what a cubic polynomial looks like on a graph. The standard equation, ax cubed plus bx squared plus cx plus d, is simply the mathematical blueprint for that roller coaster track. The letters a, b, c, and d are just placeholders for the numbers we'll eventually plug in. We call those coefficients. And what about those Greek letters, alpha, beta, and gamma? Honestly, don't let them scare you. They are literally just the three hidden keys, known as roots or zeros, that pinpoint exactly where our roller coaster crosses the ground level, making the whole equation equal exactly 0. Let's tackle our first example together, a nice easy one to get our feet wet. The question gives us the equation p of x equals 2x cubed minus 5x squared minus 14x plus 8. And it also gives us its zeros, 4, -2, and 1/2. So what is actually being asked here? Well, we need to find the hidden pattern connecting these given zeros to the coefficients, 2, -5, -14, and 8. Instead of jumping straight to memorizing formulas, let's solve this step by step and discover the pattern ourselves. Step 1, we simply add the given zeros together. 4 plus -2 plus 1/2, and we get 5/2. Step 2, we look back at our coefficients. If we take the negative of our b value, which is -5, and divide it by our a value, which is 2, wait a second, we get 5/2, the exact same fraction. This isn't just a coincidence, it's a beautifully consistent mathematical pattern linking the roots of our equation right to its core structure. I promised you we wouldn't just memorize things today. I really want you to understand why this works. This is the actual engine of the math. If you take those three zeros and write them out as basic factors multiplied together, so x minus alpha times x minus beta times x minus gamma, and you do the hard work of expanding all those brackets, you naturally create an equation that clumps the alpha, beta, and gamma together in very specific ways. The math naturally lines up the sums and products of our zeros right into the exact slots for our b, c, and d coefficients. And the actual formal derivation from our source text is the real proof in the pudding here. It confirms that the pattern we just noticed with our 5/2 fraction in that easy example wasn't just a lucky break. It is an undeniable mathematical law. By equating the fully expanded version with our general blueprint, it completely proves exactly how the coefficients a, b, c, and d are inextricably tied to those zeros. Okay, so the crucial point is learning how to extract these formulas. But I need you to listen very closely right here, because this is the #1 most common mistake students make in board exams. Watch the signs. Notice that both the sum formula, alpha plus beta plus gamma equals -b/a, and the product formula, alpha times beta times gamma equals -d/a, have a negative sign firmly built into them. You absolutely must bring that negative sign with you every single time you use the formula. No exceptions. But tucked right in the middle is our second rule. This is the sum of the products taken 2 at a time. I know it sounds like a mouthful, but think of it as just mixing and matching pairs, multiplying alpha and beta and gamma and alpha, and adding them all up. The formula for this is simply c/a. Notice what's missing. There is no negative sign here. It is completely positive. Let's pause and look at a hard, board exam level scenario you might encounter. Often, a really tough question gives you only the sums and products, those values usually on the right, and asks you to work backwards to find the underlying equation. So, What is given? The sums. What is asked? The polynomial itself. Let's solve it mentally. If a question tells you the sum of zeros is -3, and we know a is 1, you plug that into our negative b over a formula and reverse engineer that b must be +3. Look at the first row of our setup, x cubed plus 3x squared. It matches perfectly. Practicing this kind of reverse engineering is how you build true, unshakable confidence. All right, now for a medium-level problem exactly like a standard exam question you'd see. Example 7 gives us the polynomial p of x equals 3x cubed minus 5x squared minus 11x minus 3, and 3 potential zeros. 3, -1, and -1/3. What is asked? We need to verify if these 3 numbers are actually its true zeros, and then verify their relationship with the coefficients. We're going to take this one calm, simple step at a time. First up, we test our first key, the number 3. We simply plug in 3 wherever there is an x in our equation. 3 cubed is 27. 3 squared is 9. So we get 3 times 27, minus 5 times 9, minus 11 times 3, minus 3. Working out that basic arithmetic gives us 81, minus 45, minus 33, minus 3. And beautifully, if you subtract all that, everything cancels out to exactly 0. So our first 0 is officially verified. Next, we carefully plug in -1. Now here is another massive trap where students lose points in exams, so keep your eyes peeled. Pay close attention to how negative signs act when squared or cubed. -1 cubed stays -1, but -1 squared, that becomes +1. So our equation becomes 3 times -1 minus 5 times +1 minus 11 times -1 minus 3. That simplifies to -3 minus 5 plus 11 minus 3, which, once again, lands safely at exactly 0. Finally, we have the fraction -1/3. Please don't let fractions scare you. The mathematical rules do not change at all. Just take your time here. When we plug it in, we cube the -1/3 to get -1 over 27. We square it to get +1 over 9. By multiplying the coefficients and finding a common denominator of 9, we get -1/9 minus 5/9 plus 33/9 minus 27/9. Combine the numerators and it perfectly equals 0. We have successfully proven all 3 zeros. So, we've completed the first half of the exam question. We've proven 3, -1, and -1/3 are definitely our zeros. The second half asks us to verify the coefficient relationships. A quick tip: before doing any math, always explicitly list out your coefficients from the original equation. We clearly state a equals 3, b equals -5, c equals -11, and d equals -3. Writing this out guarantees you won't make a silly substitution error later. Let's move to our final verification and see how this all builds together. Step by step, we check the rules. The sum of the zeros is 5/3, and our formula, -b over a, is -5 over 3, which is also 5/3. It matches. We do the exact same for the sum of products, getting -11/3 on both sides. And finally, the product of the zeros gives us 1, and -d over a gives us 1. It perfectly matches across the board. We have proven our logic is absolutely flawless. To wrap up everything we've learned in this explainer today, let's lock in a 5-point cheat sheet. Take a mental snapshot of these rules. You have your general form, your sum formula, your sum of products formula, and your overall product formula. And, as promised, here is my surprise trick to help you solve faster and avoid mistakes in exams. Just remember the alternating sign pattern. The formulas always go negative, positive, negative. Negative b over a, positive c over a, negative d over a. If you remember minus plus minus, you will never get lost. You've just conquered cubic polynomials by uncovering their hidden logic. You didn't just memorize, you actually understood the why behind the how. But it begs a pretty fascinating question. Math is all about escalating patterns, right? If we just solved the alternating pattern for a third-degree polynomial, how deep does this rabbit hole go if we add an x to the fourth power? Think about that the next time you see a long, intimidating equation. Until next time, keep questioning and keep learning.